Well, thank you for coming out this early by astronomer standards on Saturday morning. Nice to see so many faces in the audience. And I will be talking, as advertised, about the growing pains of young stars. And wanted to start by thinking about how this ties to this year's theme of astrobiology. And my first thought was a rather pithy quote from Carl Sagan that said, if you want to make an apple pie, you must first invent the universe. Excuse me, if you want to make an apple pie from scratch, it might be an important detail. First of all, he's right. And second of all, that's part of, I think, what motivates looking at how stars form, to think about how planets form and how life might form on those planets. So with that in mind, maybe doing the apple pie experiment in reverse, I wanted to start by thinking a little bit, about life itself. So this is the tree of life, a relatively recent representation of the known diversity of life on Earth. So you see there are tons of little, I guess, hairs on the edge of this circle towards the edge that represent individual species. And then there are branches coming off of this that sort of show some of the interconnectedness of these different species of life. And they come back to what seems to be a relatively few branch points. And there's actually quite a bit of evidence that makes us think that maybe there's a common origin for life on Earth. Despite the diversity of things that we see, both in their size, their numbers, the kinds of environments that they can live in, life has a surprising number of things in common, at least life on Earth. So if we're staring at our own navels as a way to sort of figure out what we're looking for, if we're looking for life on other planets, it might be useful to think about what features life on Earth has in common that would give us a definition for life. And that seems like it could be dangerous territory to walk, to say that this is definitely life and this is not life. For example, there are things like viruses that certainly affect humans who catch them, and that can wreak havoc on their hosts, but can't seem to live independently of them. So I think there's still a question as to what exactly is alive and what isn't alive, and I will defer to my colleagues in biology to sort of get into the nuances of that. But I think there is some value in trying to write down a definition of life, if for no other reason that if we're looking for life on planets that are not our own, if we agree on a set of criteria that we can point to say yes or no, we found it. And I think there is some value in that. But I think also we should tread carefully, as I think we learned about 10 years ago when the International Astronomical Union, the IAU, sat down and wrote down the definition of a planet. Now, for those of us who grew up with Pluto as a planet, this seemed to be possibly contentious, because we grew up with 9 planets and now there are 8, because according to the International Astronomical Union, to be a planet, you must be a celestial body that A, is in orbit around the sun, B, has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium or nearly round shape. Basically, if you're big enough to hold yourself together by gravity, you'll be round. That's a long way of saying that. And then C, you have to clear the neighborhood around its orbit. So if you're plowing through a bunch of junk every time you go around the sun, you're probably not a planet. So what this did was draw a line between the 8 planets that are still called planets on the top of this graphic, and smaller things that are now dwarf planets on the bottom of this graphic. So the largest body in the asteroid belt, Ceres, is a dwarf planet now. Pluto's been demoted to a dwarf planet. And all the interesting things we're finding way out in the Kuiper belt, all these other rocky things way out past the orbit of Neptune, are also these dwarf planets. Now, there might be room to discuss what the proper definition of a planet is from here, but at least as we're finding more things, we have a set of criteria to point to say whether or not what we just found is in fact a planet. So I'm not going to lay down the specific criteria for what we should point to say this is life. Again, I will defer to somebody with maybe more expertise in biology for that. But I will think about some of the things that we notice to be in common about life here on Earth as things that we might think about motivating the study of stars to get to life on our and other planets. So, for my purposes as an astronomer, I can think of 2 things that are very key to life here on Earth that we think might be essential to life elsewhere, given how much of life on Earth depends on these things. That would be water and organic molecules that contain carbon. So our planet is famously blue because of our liquid oceans here. And we, as humans, depend on chemistry and carbon-based chemistry for energy sources. And in fact, most life needs some source of fuel from carbon molecules. It doesn't have to be Washtenaw dairy donuts, but I'm not going to be sad that that's part of the Saturday morning physics experience. So if we're looking for the criteria of life, we want to look for these ingredients when we're looking for planets that could harbor life elsewhere in our universe. So fortunately, we see these things in space. Water is a relatively simple molecule, shown here on the left. It's an oxygen with 2 hydrogens. And we see that in space. We see it on our own planet. We see it elsewhere in our solar system. We see it around young stars. So that's good. The other thing we need is complex carbon chemistry. So I've shown an image here on the right from the National Radio Astronomy Observatory of a couple of different complex organic compounds. These are different sugars that are very helpful if you want to, say, stay alive and stand in front of a group of people and possibly talk too fast at a Saturday morning physics. The simplest one here on the upper right, glycoaldehyde, has actually been detected in space. But you'll notice that it's much simpler than some of the other sugars. So it seems that we do need some space for chemistry to happen in space in order to get from these simple sugars to the more complex sugars that we think are relevant for life. So in terms of the elements that make up these compounds that we're looking at, we have hydrogen, we have oxygen in the water and also in the organic compounds, and then carbon is an essential component of the organic molecules here on the right. So if we think about the periodic table, which might be familiar from chemistry class or from the shower curtain in the Big Bang Theory, there's an incredible diversity of elements that we know about in sort of our earthbound environment here. But as an astronomer, I don't worry about most of the things on this table. An astronomer's periodic table is going to look somewhat simpler. So hydrogen is the name of the game. Helium is also present in significant amounts. And for an astronomer, everything else that is not hydrogen and helium is a metal because it's too big to be hydrogen or helium, and it exists in such small amounts that we just that's the everything else. That's about 2% of our universe. So the size of the hydrogen and the helium on this plot are suggestive of their abundance in the universe. They also have this pie chart that maybe shows that in a little bit more detail. So hydrogen is the big Pac-Man size wedge there. Helium is most of the rest of it. And then we have to zoom in to see everything else in the universe. So this is what we have now. And it took us about 13.7 billion years of cosmic evolution to get to this composition, from a universe that started out basically hydrogen and helium. So astronomy can tell us something about how we create these tiny wedges of things that are heavier than hydrogen and helium in this pie chart. And I'll just point out, if we're looking at the most abundant things, the elements that have the largest numbers in our universe, those are hydrogen, helium, oxygen, and carbon. Which, if we're trying to make molecules that are essential for life, including oxygen and carbon, it's good that those are going to be among the most abundant things in our universe. So there's another part of this story, and it's not enough for these elements simply to exist. As we are perhaps rather familiar with here in Michigan, water's physical state depends on temperature. So at the moment, I might be splashing through puddles to get to work, but in short order, I'll be trying not to slip on the ice, because temperature matters. So it's not enough just to have water on your planet or on your livable world. It has to be liquid water. This seems to be very important for transporting nutrients, biologically speaking, and all life that we know of on Earth depends on water to live. Now, we could consider the possibility that some other liquid would allow life to survive. Again, that's a little bit outside my area of expertise. More familiar to me, though, is the idea that how close or far you are from your star is going to affect how warm or cold your planet is, modulo some other effects like greenhouse gases that will help trap heat onto a planet. But what this plot shows is stars here on the y-axis, so lower mass stars, which are a little bit less bright and less warm towards the bottom, and bigger, brighter, warmer stars towards the top. And then the distance of the planet from the star here on the x-axis, so planets that are very close to the star are sort of going to be close to the left edge of this plot and further away, with this blue stripe through the middle showing the region of temperatures where water will be liquid, including our Earth. So again, if we're thinking of liquid water as being an essential component, how close or far you are from the star is going to affect whether your water can be liquid. And what kind of star you have is going to affect how close needs to be and how far needs to be. So this is sort of one of many arguments that we should look to our own planet and our own solar system as a starting place for what we're looking for elsewhere. Because we know that certain things worked here, and with our data point of 1, why not use that as our starting assumption? So, looking at the structure of our own solar system, there are a few things we might notice. All of the planets are more or less in the same plane. They're not all over the place, except for Pluto, which kind of is. But more or less, we have these planets out in a line. And we'll notice not only their geometry, but how they move around the star. So we might think about what this tells us about how these things formed if everything's sort of in the same plane and moving around the star in the same direction. It's perhaps easier to watch the motions of planets in our own solar system, but it is actually possible to check whether or not the planets move around another star in the same direction that that star rotates through something called the Rossiter-McLaughlin effect, which carries the name of the two astronomers at the University of Michigan who worked this out, Richard Rossiter and Dean B. McLaughlin. So nice Michigan connection there. Anyways, so we can look at our own solar system and be like, aha, we know some things about what conditions would likely create this arrangement and these kinds of planets. Would we expect that to be representative of what we find elsewhere? So if we start looking for extrasolar planets, and we have been, and the rate of discoveries has been exploding, we turned out to be pretty good at finding them in an incredible diversity of ways, an incredible diversity of planets that don't look a whole lot like our solar system. So this is another plot here, this time showing the planet mass. So little planets are going to be towards the bottom of the screen, and big planets are going to be towards the top. And the distance from their star is shown here on the X. So things that are close to the star are going to be closer on the left, and things that are far from their star are going to be over on the right. And you notice I put Earth and Jupiter and Neptune just for comparison. You notice we have a lot of planets that are near their stars that are big. And then we do have some planets that are far away from their stars, but not nearly as many as we have close to our stars. So we can find a whole host of exosolar planets and extrasolar solar systems, planets around other stars that don't look like our own solar system. So we might be a good starting place, but we're certainly not the whole story. So in trying to think about how you create this incredible diversity of planetary systems, it's useful to think about how they form. And forming planets, especially if the International Astronomical Union is going to demand that a planet orbits a star, means that we have to consider star formation. So that's sort of my wheelhouse, and thinking about how we go from the raw materials of a star, a cloud of gas and dust, and how we get out a star that has a system of planets orbiting around it. So fortunately, telescopes are very useful in this regard, and we can go out and actually observe all the sequences that seem to be important for putting together a star in a planetary system. So first off, we need the raw materials. We need big clouds of gas and dust, and if they block out the light of the stars behind them, as in the case of this particular cloud, that's pretty suggestive that you have a big mass of material blocking a whole bunch of light. So that's good. It's not clear whether or not this particular cloud is collapsing and going to form a star. And trying to figure out why or why not a cloud decides to form a star is still an area of interest and active research. But when they do collapse, and we know they do because we have stars, something that's very, very large collapses down into something that's pretty small. And it might be a little bit hard to see on this cartoon, but there's some arrows indicating that this big cloud is rotating. So that's going to collapse down to something littler, and it's going to spin a little bit faster. But because it's spinning, that means it doesn't just collapse to a point, but it actually collapsed to a disk. So you get something flattened and sort of spread out that's around the star. And this is useful, one, because it feeds the star material, and two, you have to figure out how to get rid of that angular momentum that's going to force that disk shape in order to put material onto the star. So we can observe that this is going on with something like the Hubble Space Telescope. Because you've made your disk out of all this gas and dust, that's still going to be sort of a thick wall of stuff blocking the light of the star. And in fact, that's what we see in this image on the right. These dark stripes here are actually the disks around stars, blocking the starlight. But they're not sort of big cocoons covering the entire star, because we can see some of the light coming out on either side of this disk. And again, this is the kind of incredible data possible with the Hubble Space Telescope. And my 5-year-old self is still delighted that we can actually see these bitty little things. So this is looking at sort of the edge of this flattened structure. If we look at it rotated, so we're looking at sort of the big flat face here, that might look a little bit different. So for this image that we're looking at on the upper right, we're looking at, again, the light that this big disk has blocked from some source coming in the background. So where it is dark, you know there's stuff blocking light. And for reference, there's a little yellow circle here showing the orbit of Neptune. So that's now the most distant planet in our solar system. Our entire solar system fits in that little circle. So there's quite a bit of stuff in this disk. It's actually a pretty big thing. And that's good because it's feeding the star. The star has to grow up somehow. But it's also the site of planet formation. And with new observatories like the ALMA Observatory in Chile, we're starting to be able to look at these disks directly and in great detail. So this is an image of H.L. Tau here on the left. Astronomers have just the best names for things, don't we? You can start to see some of the structure in these disks. There are these rings around in the disk. There are gaps around in the disk. And this is very exciting because you think if you have a planet growing up in this disk, gobbling up material, it might carve out some of these structures. So that's cool. I cannot confidently say that there are planets forming in this disk because it turns out chemistry can kind of create some of these same structures. This is a very active area of research here at the University of Michigan. But while we're still working out the details here, we know that planets certainly do form, probably in these disks, because we see them. So these were some of the very first directly imaged planets. So we had seen some indirect indication that planets were there before, but to actually get a picture of them, these were two of the first. I guess, Eye of Sauron, if you're into the Lord of the Rings. On the right is the planet found around Fomalhaut, and on the left here is HR 8799. Again, we have great names for things, showing 4 different planets orbiting a star. So one, we see these bright things near a star. That could be bad luck, right? If I have a flashlight here, which is very faint, and a floodlight here, which is very, very bright, and I hold them next to each other, it's going to be hard to see things. I could be unlucky and have a floodlight here, and then run to the back, and in the poor person in the last row's face, just hold that flashlight and say, okay, which is closer? It would be hard to tell. But in both of these cases, we actually see these planets moving, and they're orbiting their stars. So this sort of, at least this much that we have planets orbiting a star, looks like our solar system. These planets are kind of big and kind of far. Again, we have sort of a lot to learn about how you create the full diversity of planetary systems, including, but not limited, some really weird things that are like really far away from the stars where they formed. So if we're looking at a star here on the lower left, and again, that green circle shows you the orbit of Neptune, so the most distant planet in our solar system, and we go and find something, as Vanessa Bailey did, HD 106906b, which is a 12 Jupiter mass planet that's 650 times further away from its star than the Earth is from the sun. So 1, that's cool, and 2, that's really far away from its star. And if we think back to that big disk that we saw forming around a star, it's big, but if I compare the circle showing the orbit of Neptune in that disk to the circle showing the orbit of Neptune around that star, it's really hard to imagine how you make a planet in that disk and get it all the way out there. But life is long for people and for planets. And as somebody who grew up in California and now lives in Michigan, it is possible people move and planets move. So maybe it's out there now, but maybe that's not where it started. But clearly we have a lot to learn. But I think these basic details are sort of what we need to consider, in that you got to start from this raw material. When you're forming your star, you form this disk, and that disk is the site of planet formation. And we know that's got to happen because we see the planets now. I like this cartoon as a summary picture, although it's a little bit old because it says indirect tracers. And that's not really true anymore. We've been able to observe every step of this process, from the raw materials to these disks seen in silhouette, to these disks themselves, and sort of picking out how the planets are forming within them, to the planets around other stars. So what's missing? Sorry, say louder. People, right? So we don't have evidence for people on any of the planets that we've seen around other stars. And I actually like the idea of thinking about people as sort of an analogy for what else is missing from this picture. So, there's very nice biographical introductions include where I went to college and where I went to graduate school and some of the things that I have done in my career. And it doesn't sort of give credit to, say, some of the people who mentored me along the way, some of the people who have significantly shaped my career in their quiet ways of being in my life. And so I like the idea of stepping away from this picture of a star as a solitary thing and thinking about stars as part of larger communities within the universe. And part of that is sort of my romantic idealism of interconnectedness of things. And part of that is because 90% of the stars in the universe form in big, messy complexes like this, and not all by their lonesomes from these little clouds that were all by themselves. So if we want to think about how the vast majority of stars form, and by inference, probably the vast majority of planets, we need to think about these big, messy environments where things are close together, and they're going to know about each other, and that's going to affect their formation and evolution. So there are a couple of things that we need to consider that are possibly going to complicate the picture, although in my eyes, that's just going to make things more fun. And one of that is that there are different types of stars. So our sun is a G-type star, shown here on the left. We're sort of mid-size, bright but not too bright, warm but not too warm. You notice there are letters labeling these different types of stars, and it seems to be a pretty illogical order. So when we were first looking at different types of stars, we were trying to figure out what was going on. So we ordered them. There's A-type stars and B-type stars and C-type stars and D-type stars. And then we figured out the physics going on underneath and reordered everything according to the physics behind them. And now we end up with O, B, F, G, K, M, L, T. So for the purposes of our discussion, we can sort of think of these in sort of broader brushstrokes of sort of big, bigger, biggest stars, which you'll notice are actually color-coded in my slide and also in reality, that the littler stars here on the left are red, and the bigger you get, the bluer you get. So the biggest stars are very blue, like the star on the right, and the bigger stars are bluer because they are hotter, because they have more mass. And because of this, they will live their lives much faster than the little stars, and they will die more explosively than the little stars. And because of reasons that we still don't fully understand, when the universe is making a cluster of stars, it will make relatively few of these big blue stars. And for every one of these big blue stars, it will make thousands of these littler, redder stars. Still trying to figure out why that is the case, but it is something that we observe to be true. So, if we're thinking about clusters of stars, I'm talking about stars that are going to be living, say, 10 million years in the case of these big blue guys, versus 10 billion or more if you're a star like the sun. And I can talk about how you can have hundreds of O-type stars, these big blue stars, and you could have millions of these low little red-type stars. And I'm throwing around these enormous astronomical or economical, if you prefer, numbers without really grounding them in reality. So I think it is worth our time to take a moment just to think about how big some of these big numbers are. So if I draw a number line here and I put 0 on one end and a billion on the other, where is 1 million?
Way over at the left.
Way over at the left. Does anybody disagree? No. All right, this is a mathematically literate crowd, yes. So 1 million is going to be right next to 0 here, because 1 billion is 1,000 million. So I actually tried to slice up this line on my slide into 1,000 pieces and figure out how close to the edge to put the arrow. And then I decided it was better to use a line thickness big enough to see. So it's right next to 0. So if we're thinking about the lifetimes of stars that are forming all in one big clustered environment, if I have a star, a very big, massive blue star, that's going to live for 10 million years, that's actually not that long compared to a billion. And if I have a star like the sun that's going to live for 10 billion years, we're talking actually about a pretty big difference. So just to try and, again, think about this in terms of human timescales, 1 million seconds is about 11 days. 1 billion seconds is just shy of 32 years. Yes, exactly. So if I'm thinking about a very massive star that's going to live for 10 million years, so what is that, 110 days on human timescales? What's that, just over 3 months, something like that? 10 billion years for a star like the sun is 320 years on human timescales. So if we're making a cluster of stars that has these different types of stars in it, some of those are going to be gone in months, and some of those are going to be around for hundreds of years, again on human timescales. We've got this all mixed up into one group. So, one, astronomical numbers are big. And two, sort of thinking about what that means for everything else going on in this cluster, right? We've got these things sort of close enough to know and care about each other. And that may not be obvious to the naked eye when we look up at a cluster, say like the Pleiades, the 7 sisters, although I've only ever seen 6 of those stars. And we're only seeing the brightest of the stars in that cluster, but if we have a telescope, and fortunately we do, we can look at the Pleiades and see it's a lot messier than that. You can see there's some emission from lots of gas and dust still in this region. And you also notice there's an awful lot of stars here. So this region's about 13 light years across, and there's something like 3,000 stars here. For reference, we are orbiting one star, the sun. Our nearest neighbor is 4 light years away. So in a region about 3 times bigger across, there are something like 3,000 stars. So it's cozy if you're forming in a star cluster. And close enough in some cases that stars would know about their neighbors as they're forming and as they're growing up. So maybe instead of just thinking about this cartoon picture of taking this one nice isolated cloud and turning it into one nice well-behaved star, we really should be thinking about the messier picture of turning a big cloud of gas and dust into a cluster of stars. Now I have a question. How do I convince my big cloud of gas and dust to form a cluster of stars instead of forming one big star? Yeah.
Maybe different regions, as they're forming, maybe different regions at different temperatures.
So maybe different regions have different temperatures or
Densities or different whatever.
Yeah, so you're on the right track, exactly. Different regions could have different physical conditions that are going to affect what forms there. The other thing is these very massive stars are sort of oddly social. It turns out to be very hard to form one and only one big star. If you form one very big star, you almost always have a bunch of little stars with it. So forming a big star means you're forming a cluster of stars. So if we're trying to pick apart this process, like, okay, I'm going to go look at a cluster of stars and try and figure out how this all fits together, what is the tool of an astronomer to do this? I'll give you a hint. Light. Light is the only thing that comes to us. So if I'm sort of looking out at the audience, I can get the rainbow of colors shown here on the screen. That's the kind of light that is available to my eyeballs. But if we look at this graph at the very top of the screen, showing different types of light, you'll notice that what our eyes can see is only a small fraction of all the light made in the universe. Which means that if we as astronomers can use a diversity of different types of light, we can probably get a pretty incredible view of things. And thanks to the physics demonstration lab, we actually can play that game a little bit right now by looking at an infrared camera. All right, let's do the intermediate case then. If we're sitting on this side of the room relatively near the light and we're looking at this part of the audience, is it going to be easy to pick apart, say, what color shirts people are wearing or the sorts of things that make individuals distinguishable from each other? Not really, no, right? Because we depend on light to do so. But if I take my infrared eyeballs here and I spin it around to this side of the room, hi, people. Everybody's really bright, yeah? So if we had infrared eyeballs, humans glow in the dark. That's cool. That's fun stuff. So if I'm thinking about how this might be helpful as an astronomer, can you think of anything else that might be warm and glowing but still hidden in something cold and dark?
One sec, I want to get a shot.
All right. All right. I hear circumstellar disks. So yeah, if I'm, hi Monica. So if I spin around here and look at this black screen, do you see much of anything in there? Yeah, there's a little bit of texture and structure because things are going on. But looking at it with the infrared camera at the moment doesn't tell us much, but watch what's happening as we have flipped the switch here. And sort of think about what else might be going on in these kinds of regions. Anybody see anything?
An M-shaped region on the lower side of the picture being
Go blue? Yeah? But you notice something is glowing inside of this screen here. Can we flip the room lights again? With our eyes, can you see anything inside this trash bag? No. Right? So infrared light is very useful for somebody like me who's looking for warm things that are hidden behind, in my case, a bunch of gas and dust. So, cool. Can we switch back? Awesome. Thank you. Perfect. Sweet. So if we go out looking at our own galaxy and trying to put together all the different pieces that we need to make stars and planets and life, these different colors of light are going to be very helpful to us, and fortunately we have the technology to go looking for this. So this is a view of our Milky Way, thanks to NASA, and each of these stripes is our Milky Way in a different color of light. So less energetic light is towards the top, the radio continuum, and more energetic light is towards the bottom, the gamma rays. And each of these different types of light is giving us different information about what's going on there. So a couple of things that I might look towards is molecular hydrogen here, which is the 1, 2, 3, 4th one down. That's a very important raw material for stars. And you notice that's all nice and flattened, sort of in the plane of our galaxy here. I might also look at, say, some of these infrared panels, the 3 panels below the molecular hydrogen. We can see things glowing. If you make dust warm, that will glow. If you heat dust up, because you have a young star in there, it'll start to glow. And then all the way down to the optical here, that's the 3rd one up from the bottom. This is the light that our eyes can see. So stars are bright in the optical. But do you notice something going on in this picture that doesn't just look like a stream of stars? What do you see? Dust, right? There's all kinds of dust out in space. And in this case, it's blocking the starlight. And on the one hand, we could say that's a bummer because we can't see the stars. On the other hand, we can say wahoo because we have the stuff to form more stars. And that is job security for some of us. So, woo! So by playing around with these different types of light, we can start looking into these star clusters and looking not just at the gas and dust as we see with our eyes, but also see all the stars embedded within them. So my favorite place to do this is in the Carina Nebula. So compared to some more familiar, say, high-mass star-forming regions that might be familiar from the northern hemisphere, like Orion, the Carina Nebula is further away. It can only be seen from the southern hemisphere, but it's a big thing. So this is an image and sort of light that our eyes can see of the whole big star-forming region. It's about 3 degrees on a sky, and it's huge, and it's full of stuff. You can kind of see there's this weird V-shaped dust lane in the middle, and then there's all this bright stuff everywhere. But that view is going to look a little bit different as we use different colors of light to look at this thing. So as I step through here, going to longer wavelengths, so things that will tell us about some of the dust in the region and raw materials for more stars, you notice, one, the picture gets a little fuzzier because it's hard to get sharp pictures at long wavelengths, and 2, that the structure of this thing looks very different. Now, one of my favorite ways to look at star-forming regions is with the Hubble Space Telescope, partly because we put a telescope in space and, dude, that's cool, and partly because of how incredible the data we get out of that is. So if we zoom in on just this central region of the Carina Nebula, we have this beautiful mosaic that came out of the Hubble Space Telescope. I was just going to pause for a minute because this is one of my absolute favorites. So this nebula has everything in it. So just to step through, again, just in this sort of central region, all the things that we have, and sort of pick together why we care if we're trying to form life at the end of all of this. But before doing that, just to make one more case for the Hubble Space Telescope. So this is an image taken from the ground of a portion of the Hubble Space Telescope, and that looks pretty cool and pretty interesting, but it doesn't compare to the sharpness of the images that we can get if we go above the atmosphere. So this picture here is actually taken with a bigger telescope, but it's on the ground, and the smearing of the atmosphere is kind of going to fuzz it out. Ooh, I went too far, thank you, sorry. The bigger telescope still can't overcome the smearing of the atmosphere without additional technology. But if we go above the atmosphere, the incredible sharpness that we can get from the Hubble Space Telescope lets us start putting the pieces together of everything that you have to consider for a star forming in this kind of region. So some of those things are the fact that you're going to have some stars, those very big stars that live fast and die young, are already all grown up. So you can have a cluster of these stars. These are some of the most massive stars in the region. You have a bunch of dust and other stuff. This is part of that big V of dust we saw in the big image. That's the raw material for more stars to form. It's not a guarantee they will, but at least we have this stuff to do it. And in fact, we do have some stars forming. This is that complex we were just looking at, comparing the Hubble Space Telescope image to one we get from the ground. And there's reasons that tell us that there must be stars forming in there. You know, some of these big massive stars are this close to dying. So this star right here, Eta Carina, is one of the most massive stars known in our galaxy, and will go supernova in the astrophysically near future, which means it could go supernova tomorrow. It could go supernova 1,000 years from now. That's still astrophysically soon. And then we have these things that look like what we think our solar system might have looked like at the time of formation. Again, if 90% of stars form in big, messy regions like this, there's a chance that our sun might have been one of them. So just thinking about all the things a star forming in this environment has to contend with, one is going to be erosion, right? We have all of these big, bright stars here, something like 65 of the biggest stars the universe makes, blasting everything around it with winds and radiation and all these crazy things, which could be bad news for a forming star, but also lights all of this up so we can see it. So that's cool. But if we look at some of what that creates in the nebula, like these sort of finger-looking things on the bottom that are pointing almost towards these big stars up here, you notice they kind of look like some of the, what are these, buttes here from Monument Valley? And in fact, it might be much of the same erosive process. So in these earthbound systems, we think you need some sort of caprock or something to prevent further erosion in these few areas where the rock is much higher than the rest of the area. And so it may be true in these dusty regions here. You might have some very dense stuff, like the stuff that will become a star, protecting erosion behind it so that everything else gets blown away, leaving these sort of elephant trunk-like things pointing towards the stars. And that kind of erosion creates a whole diversity of things living out in the nebula. And some of those we think are forming stars, like the one up in the left. Some of those it's a little bit less clear. They're all kind of blobby and weird and interesting looking and fun to think about. We can anthropomorphize all we like. Say, look at this guy that looks an awful lot like my brother, given the hook 'em horn sign when he got into the University of Texas. But you know, it's worth considering if we have these blobby things that are surviving out there in the big messy environment created by these massive stars, how do they stay alive at all, right? If I'm talking about all this destruction because of the winds and the radiation, it's not clear that these things should stick around long enough for us to see them, especially if some of the big, bright and most destructive stars have lived long enough to be almost dead already. So one option is that if you have a star forming in there, that will help you fight against this kind of erosion. So to look back at this region of forming stars, this might be a familiar region from that black and white image, just to look at it in color. There are some clues that there are stars forming, helping protect these pillars from further erosion. And one of those clues is the jets that we see coming out them. For reasons that we don't fully understand, when you have this disk forming around a star, you also get a jet coming out. So the fact that we can see these jets, even though we can't see the disks, tells us there's got to be a star forming in there that's forming these jets. So that's cool if that's right, but what are the odds that we were just unlucky and it looks like a jet, but it's not really a jet? Well, one thing that we can do is go back and take another picture, either 5 or 10 years later, and by blinking back and forth, as we're doing right now on the screen here, I can try and look and see if these jets are moving. Are they moving? Yeah. Do you think they're moving very fast? No? No? So I hear some no's and some yeses. So there's one tricky thing about looking at regions like this that are big and messy. They tend to be far away. So if I think about something like Orion, that's one of the nearest regions of massive star formation. So the Carina Nebula, where we're looking for these pictures, is about 4 to 5 times further away, which means that we're going to be looking at across a much further distance, and things that are going to be moving are going to appear to be moving not that much. Right, so between image number 1 and image number 2, these blobs have moved a little bit, just a little bit. That's actually about 500,000 miles an hour of motion, but it only looks like a little bit. So because these things live very, very close to these very big, bright, massive stars that are doing some destructive things, if we start putting the pieces together, it would suggest that the star might be an important part of protecting against that. Although if we're looking closely at these images, I would argue you can see the star at the center of the jet on the one on the bottom, not at the top. But the one at the top is the one that's at the tip of this pillar here in the box, right next to those big, bright stars. So one thing that might be happening here, I think is best described by a cartoon from the Foxtrot cartoon some years ago. So in Foxtrot, for those who are not familiar, there are a couple of siblings who give each other a hard time. So Paige has some cotton candy that she got at the fair, and her brother Peter wants a bite. So Paige has her fluffy cotton candy, and she tells her brother, 1 bite. So Peter proceeds to take the cotton candy and wad it up into this nice small little ball. And when it is all down to the size of, say, a gumball, he's like, all right, time for my 1 bite. So it might be possible that actually something like that is happening here. All of these stars are pushing hard against what used to be a sort of fluffy cloud. And while it's all wadded up, you might have something tight enough and dense enough to hide the star in it completely, right? We saw that if we put something that will block the light our eyes can see, something might be hidden from our eyes. If we put even more stuff, we might even hide it from the infrared camera. But because we see the jet, we know there's got to be something there. So the other thing thinking about these stars forming nearby is thinking about stars, again, not forming all by themselves. So partly these are going to know about their older siblings, pushing them around a little bit. But even for stars that form in a cluster, it's worth thinking about how these might interact with each other. We have snapshots in time telling us what these regions look like. But again, life is long for us and for star-forming regions, so things can move around as a function of time. So just to take a simulation here from Matthew Bate at the University of Exeter, showing how the gas in a star-forming region might move around, you'll notice that there's sort of a lot of structure here of red in this case showing sort of low-level emission from gas, and then the brighter yellower stuff is where there's a lot of gas sort of clustered up. So as we hit the play button here on the simulation and watch this all evolve, you notice the gas is moving around and sort of gathering up in some places, and not so thick in other places. And maybe if we're watching carefully, we can see a couple of bright, almost white things show up and start moving around. Those are the stars. Remember, stars are born out of gas and dust. And so as they're forming from this cloud that's evolving, they start moving, and they're moving all over the place. And they're interacting with themselves, with the gas, with each other. So over the course of the evolution of this cloud, stuff's going to change a lot. So even the snapshot that we've been looking at in the Carina Nebula is not the whole story. So I like this particular view of star formation because it shows all the stuff that's going on. It might be easier to see how much the stars get moved around by looking at the same version of the simulation that just shows the stars. So in this case, it's going to look dark for a while because the gas is moving around, but we don't have that many stars. But you'll see them start popping out here. And you'll see them sort of, some of them circle around each other and some of them go flying off. Some of them sort of cluster close together and do enough to heat up the gas that we could see the gas, even though that's not the rendering we're looking at. And again, just sort of showing that there's a lot going on as you have a cloud forming. Including, say, in the middle here where you've got all that sort of bouncing bright red stuff, that's sort of like lighting up the region, like we needed the big massive stars to light up the Carina Nebula here, just so that we could see it. So we can think about the interaction of stars with their neighbors, both in terms of sort of moving around in this big region, and we can think in less complicated terms of just thinking about siblings. So not every star is going to live its life on its own, like the sun. And in fact, there are some stars that will live their lives in pairs. So you could have these binary stars, and in fact, there are a lot of binary stars in the universe. And in fact, the bigger your star is, the more likely it is to have at least one companion, if not more. So if we're thinking about forming planets, why wouldn't we think about forming planets around these binary type stars? And in fact, we have found planets around the binary type stars in the popular press referred to as the Tatooine planet for Star Wars related reasons. But thinking about, okay, if I have 2 stars instead of 1 star, what does that mean for my planet? and for that ability of that planet to host life. So there are a couple of ways to think about that. One, if your stars are very close together, maybe there's a point at which the stars are close enough together, we can just think about them as one star. But as we move them further and further and further apart, that could start to be bad news for the planet in terms of gravity kicking things around, or the stars sort of being pulled, or having trouble with too much radiation from one, or there are a lot of ways to make this messy. So it's sort of interesting to think about if we have, this situation of planets forming in a disk around a star. What happens if we actually have two stars forming there? Do we get two disks? Do we get two stars in one disk? What does that mean for the planets? Could they start around one star and end up around two? There's a whole host of things that could be going on that I will happily defer to my friends and colleagues working in dynamics. But I wanted to bring it up because there has been some discussion more recently about a possible ninth planet in our solar system that is not Pluto. So this is something that we have indirect evidence for, but have not directly detected. So something that would be pushing rocks around in the outer solar system because of its gravity that we could go out and potentially find if we were to look for it. So the question is, so how do you form some of these bigger things that are very far away from our own sun? Especially if we were talking about, things forming in this disk, maybe the disks aren't big enough. Well, again, stars are interacting with each other and moving around over the course of their lives. So it could be something like, in this clustered region, you have one star that has a couple of planets, and you have our own sun that has a couple of planets. And one star is moving past the other and just sort of wandering by, and happens to see this planet that's on a wide orbit, so not held on too tightly via gravity. And it sees this planet and says, it's mine now. And maybe that's how we got Planet 9. Maybe we stole that from another planet. I thought it was an interesting idea. Add it to our arsenal of things to consider when we're trying to figure out how you put together this incredible diversity of planetary systems. So one other thing to think about when we're forming in these big, messy regions is the fact that at least this star, Eta Carina, is about to go supernova. But all of the very big, bright stars in this region will eventually go supernova. Might take a few million years more, which again, for a 10 billion-year-old star, is pretty near future still. And in this region, we expect there are going to be at least 70 supernova explosions that go off. So that could be good news, that could be bad news, depending. So just to take a moment to think about why a star explodes at all. So the short answer is that the life of a star is a battle between gravity and whatever else the star can come up with. So gravity is always going to be pushing inward, and in this cartoon here, something is going on in that central blue circle to push outward. And in a star, that's going to be nuclear reactions. So for most of a star's adulthood, that's going to be turning hydrogen into helium. But for a very big massive star, when that energy source runs out, that star is going to work very hard to come up with anything else that it can fuse to get some energy out and to fight back in that battle against gravity. So lucky for us, the way a massive star fights back is to start fusing successively heavier elements together and fusing heavier and heavier and heavier things. So we end up with this structure at the very end of a massive star's life, sort of shown in this cartoon on the right, that's all contained in that blue center of the star. We've got this region at the center sort of fusing the heaviest elements together, surrounded by a layer doing slightly less heavy elements, slightly less, all the way out. And if we're looking at the names of the elements on this cartoon, they might look familiar from the astronomer's periodic table that we looked at earlier in the talk. So if we're looking at those elements that the star is making in its fight against gravity, you'll notice that things like iron and silicon are shown as some of the less abundant elements in our universe on this periodic table. And this is why Neil Tyson likes to say we are all star stuff. All of these elements, basically, that are not hydrogen and helium have been made in stars. So the fact that these very big, bright stars exist is very useful, and the fact that they explode is about to be very important for us and other life forms that appreciate the diversity of chemistry available to us, not just for our silicon-based devices and our love of not being anemic, but just to have sort of the components that we need for the chemistry for life. So this is a sort of zoom-in picture of the star that's about to go supernova. It doesn't look much like a star in that we expect a star to look like a point of light. And in fact, it's surrounded by a bunch of gas and dust it's thrown off in its most recent temper tantrum, which is one of the clues that we have that the end is very, very near for this star. So if we think about it, when this thing explodes, that's going to be an impact, pun intended, on the environment around it, both in terms of throwing off material and in terms of actually kicking the cloud nearby. So this could start another episode of star formation. So we don't know exactly what causes the cloud to collapse, but maybe if you kick it, then it will go. And this might be one way to do it. The other thing that is helpful here is the fact that it's exploding. So we can get all of those newly made elements from the star out and put them into the gas and give them to the stars that are forming, and say something like our early solar system, where if we look at the composition of rocks in our own solar system, there's reason to believe we had to be decently close to a supernova to lock up some of the elements made in this explosion into our own rocks to get them out. So how does the explosion of a star happen from sort of the collapse when it runs out of things to fight gravity? Well, gravity wins, right? So in the center of your star, when you've got something that can no longer continue fusing elements, everything outside of that is going to collapse, right? Gravity's winning, so that falls inward. But when it hits that inert core is when you get the explosion. So ladies and gentlemen, watch your hats and glasses as we explode our star here. And I'm sorry, we do have failed supernovas too. This is one of them. It's going to go eventually. So we'll just call that one of the pre-eruption explosions that created that sort of weird dust cloud. Let's try and explode it this time. All right, on the count of 3. 1, 2, 3. Let's hope it works. Oh, man, it's not a good day to be a supernova. All right, I'm going to keep talking, and one of these days it's going to explode. So when this thing does explode, though, it'll shoot out some of the chemistry. Yes! Did we see where it went? All right. Did we see how high it went? Yes, all right. So when we don't have gravity pulling it back down to Earth, you start to mix this into the environment, and that could be very good for the composition of rocks that we see in our own solar system, and might be very important for shaping others. So we have all of these different things going on in one region, and some acknowledgement of the fact that time moves ever forward. So this is but a snapshot in the evolution of this region. So if we're thinking about all of these different components working together, we can think about how this might help create the diversity of planetary systems that we see when we go out and hunt for planets. Especially since most of the ones that we know about don't look anything like our own solar system. Now, I should be careful to point out here, the absence of evidence is not the evidence for absence. So just because we don't see solar systems like our own does not mean that there aren't some cases that do look quite a bit like our own solar system. And some of this is a function of data collection being ongoing, and some of this is a function of our measuring techniques. So some of these things, like if we're taking an image of a planet around a star, it's going to be much easier to find planets that are far away from their star than planets that are close to the star. Because if you think about it, if you have a little rock and a big bright star, if I hold a pebble next to a floodlight, good luck telling me what color the pebble is, right? So we're getting better at hunting for planets, and I suspect that we will continue to find a diversity of forming systems. But also, if we're looking at this diversity of planetary systems, it might be worth thinking again about the diversity of life that we could be considering, looking for on our own and other planets. So even in our own solar system, if we're thinking of our own planet as a nice water-rich world, it turns out oceans are big on human scales, but the quantity of water on the surface of the Earth is not that large compared to the quantity of the Earth. As I think is nicely shown from this graphic from the astronomy picture of the day, that relatively speaking, we don't have that much water on our planet. And compared to even some of the other bodies in our own solar system, we don't have that much water. So some of the moons around other giant planets in our solar system have substantial amounts of water. Now, they're around the giant planets, so they're farther away from the sun, but they're around planets that are themselves big and sort of bright, and maybe could warm up the moons themselves with, say, tidal forces or other things that are going to keep the water liquid. So it is possible that we have life that depends on water to survive in other places in our own solar system. Let alone considering the possibility that a liquid other than water might be usable for life in other conditions. So it's sort of weird to think about looking at, say, moons around giant planets as a place to look for life, because these conditions, say, oceans under the surface, seem so extreme compared to what we're used to as humans. And I mean, to be fair, humans are a little bit particular about the kind of circumstances under which we survive and thrive, needing lots of oxygen in the atmosphere, needing water to be liquid and have the oxygen abundant. But also, we should think about our biases on what seems like an extreme environment. And I might say that as somebody who grew up in California. My family in California thinks Michigan is awfully extreme as an environment. So if we're thinking about extreme environments on Earth, on some level, those are conditions that seem extreme to us as humans that need sort of a narrow range of conditions to exist. They may not be that extreme in other places in our own solar system and other places in the universe. And I think that's worth thinking about if we're also trying to come up with a definition for life. The tree of life here shows all known species, but there are a lot of good reasons to think that this only scratches the tip of the iceberg of the diversity of life that we know about here on Earth, as we're just beginning to explore some of the more extreme regions and places on Earth and find them teeming with life. We could find a considerable increase in the quantity and types of life on our own planet, much less the types of things we should be looking for if we're going onward and outward beyond Earth and beyond our own solar system. So on that note, I guess I wanted to wrap up with a sentiment from John Donne that both in terms of stars tending to form around each other and the ways in which forming in these clustered environments might be important, and the ways in which our own planet is teeming with the diversity of life that maybe we can only just imagine, no man is an island. And with that, I'll be happy to take your questions.